Namaskar. Today I am talking on some major theories of orogenesis. Part 1, origin due to internal processes. Contents of the topic: introduction, magmatic crystallization, magmatic segregation, fractional crystallization, liquations, hydrothermal processes, sources of solutions and their contents, means of transport, lateral segregations, metamorphic processes, objectives. To understand the mode of formation of ore deposits within the earth crust involving magmatic segregation process, hydrothermal processes with special reference to sources and contents of hydrothermal fluids and means of their transport, and lateral segregation and metamorphic processes. Introductions. The theories pertaining to the genesis of mineral deposits can be broadly grouped into two categories. Number 1, origin due to internal processes, and number 2, origin due to surface processes. The first group of processes include the magmatic crystallization and magmatic segregation and precipitation from hydrothermal fluids, lateral segregation and metamorphic processes. The second group of processes comprise: number 1, mechanical accumulation, number 2, sedimentary precipitation, and number 3, residual accumulation processes, and number 4, supergene enrichment, and number 5, volcanic exhalative sedimentary processes. This lesson examines the role played by internal process in the development of ore deposits. Ore deposits created by endogenic processes include magmatic, orthomagmatic, pegmatitic, gneiss, skarn and porphyry type deposits, and deposits developed by hydrothermal cavity filling and replacement processes. Magmatic crystallizations. This covers the ordinary process of crystallization of volcanic and plutonic igneous rocks. Some of these, such as granites and basalts, are exploited as bulk materials. Others may be important for their possessions of one or more economically important minerals like diamonds in kimberlites, feldspar in pegmatites. Magmatic segregations. The term magmatic segregation or orthomagmatic deposits are used for those ore deposits that have crystallized directly from magma. Those formed by fractional crystallization are usually found in plutonic igneous rocks. Those produced by liquations may be found associated with both plutonic and magmatic or volcanic rocks. Magmatic segregations deposits may consist of layers within or beneath the enclosing igneous rocks mass subjacent to copper, nickel, sulfide ores. Fractional crystallizations. This includes any process by which early formed crystals are prevented from equilibrating with the melt from which they grew. The important process until recently were thought to be gravity fraction, fluid differentiation, filter pressing and dilations. Campbell et al. 1974, but the simple hypothesis of separation and mechanical sorting by magmatic currents invoked by various workers as being at least partly responsible for stratiform chromite accumulations were questioned. As long as in 1961 by E.D. Jackson, following his work on the layering in the still water layer complex, the critical evidence and the new explanations of deposition from density currents and in situ bottom crystallization were succinctly summarized by Best in 1982. The second type of this process is favored by Eels and Ramons in 1985 to explain evidence from the Bushveld complex, South Africa. Whatever the formative process may be, their products are the rocks called cumulates, which often display conspicuous lithological alterations called rhythmic layering. Owing to their frequent repetition in vertical sections of the plutonic bodies in which they occur, most of these intrusions appear to be funnel shaped, but the diameter of the funnel relative to its height varies greatly. The layering is generally discordant to the walls of the funnel. Usually olivine, pyroxene or plagioclase rich layers are formed. However, which oxides such as chromites are precipitated, layers of these minerals may develop as in the Bushveld complex of South Africa. This enormous layer intrusion is characterized by cumulus magnetite in the upper zone. The chromite layers have been mined for decades. The magnetite now being exploited for its high vanadium content. Detailed studies of the rhythmic layer suggested that each unit results from the influx of a new magma pulse, which forms a layer at the base of the magma chamber, which cools and precipitates a mineral or mineral phases until its reduced density permits mixing with overlying magma. The precipitated crystals are thought to be nucleated and grow in situ on the floor on the walls of the magmatic chamber. Another minerals which may be concentrated in this way, limonite, Will's chromite accumulations are nearly all in the ultrabasic rocks and to a lesser extent in graboic or noritic rocks. Illuminate accumulations show an association with anorthosites or anorthositic gabbros. These striking rock associations are strong evidence for the magmatic origin of the minerals. Liquations, a different form of segregation, result from the liquid immiscibility in exactly the same way that oil and water will not mix but form immiscible globules of one within the other. So, also in mixed sulfide silicate magma, the two liquids will tend to segregate. Sulfide droplets separate out and coalesce to the form globules, which being denser than the silicate, rich magma sink through it to accumulate at the base of the intrusion or lava flow. As shown in the figure 1, iron sulfide is the principal constituent of these droplets, which are associated with the basic and ultra basic rocks, because sulfur and iron are both more abundant in these rocks than in the acid or intermediate plutonic rocks. Chalcophile elements such as copper and nickel also enter these droplets, and sometimes that platinum group metals also partition into the sulfide droplets. A basic or ultra basic magma is generated by partially melting in the mantle, and it may acquire its sulfur at this time or later by assimilation in the crust. For significant sulfide generation to occur, the magma must be sulfide saturated. If immiscible sulfides form equilibrated with the silicate magma, settle and accumulated on the substrata in a single stage, after which the magma begins to crystallize olivine. Then we have the process known as batch equilibrium. If the proportion of sulfide form is large, much of the available nickel in the magma is removed, and if the ratio of the mass of magma to mass of sulfide is about 1000 or below, then there will be obvious nickel depletion in the magma, and the consolidated silicate rocks will carry a geochemical mark that can be used both to identify favorable exploration targets and give indication of the tenor of nickel in the possible associated mineralizations. Contrasting with batch equilibrium, we may have a fractional segregation. This is a more continual process in which small amounts of sulfide become immiscible and then settle. The silicate melt is still sulfide saturated, and crystallization of just a small amount of olivine will increase the sulfide concentration in the remaining liquid, thereby forcing some more dissolved sulfide out of solution. For the formation of an ore deposits, the timing of the liquation is critical. If it is too early, then the sulfides may settle out in the mantle of the lower crust. If it is too late, then crystallization of silicates may be in full swing and they will dilute any sulfide accumulations. The process that can promote sulfide immiscibility are cooling silications, sulfur assimilation and magma mixing. The accumulation of iron, nickel, copper sulfide droplets beneath the silicate fraction can produce massive sulfide ores. These are overlain by a zone with subordinate silicates enclose a network of sulfides, sometimes called disseminated ore. This zone is in turn overlain by one of weak mineralization which grades up into overlying peridotite, gabbro or comatite depending on the nature of the associated silicate fraction shown in figure 2. Source layering of copper, nickel, ores in comatite, flow or sill. Orthomagmatic titanium deposits in anorthosites are also considered to be a liquation of origin. Hydrothermal processes at aqueous solutions have played a part in the formation of many different types of the mineral and ore deposits. For example, veins, stockworks of the various types, volcanic exhalative deposits and others. Such fluids are usually called hydrothermal solution, and many lines of evidence attest to their important role as mineralizers. Homogenizations of a fluid inclusions in minerals from hydrothermal deposits and other geothermometers have shown that the depositional range for all types of hydrothermal deposits is approximately 50 to 650 degree centigrade. Analysis of the fluid has shown water to the common phase, and usually it has selenites for higher than that of seawater. Hydrothermal solutions are believed to be capable of carrying a wide variety of materials and depositing them to form minerals as diverse as gold and muscovite, indicating that physical chemistry of such solution is complex and is very difficult to imitate in the laboratory. It always should be remembered that hydrothermal ore deposits are small compared to with most geological features. The large ore deposits are only a few kilometer cube in volume. At first sight, they may be appear to be random accidents with little or no control over the position or geological environment in which they occur within the crust. Nevertheless, deposits can be classified into families, and individual family members occur more frequently in some areas of the crust than others. Despite their variation in the occurrence and the large number of minerals known in nature, hydrothermal deposits display in chemical constancy that is the best expressed by the limited and repetitive ranges of minerals, mostly sulfides and oxides, that are found concentrated within them. This chemical constancy suggested that relatively few chemical processes are important in their genesis. To understand the genesis of hydrothermal deposits, it is necessary to identify the source and nature of the hydrothermal solutions, the source of the metals and the sulfur in them, and driving force that moved the solution through the cast. The means of transport of these substances by the solution and the mechanism of depositions, source of the solution and their contents. There is much evidence that saline hydrothermal solutions are and have been very active and widespread in the crust. In some present day hydrothermal systems, the circulation of hydrothermal solution is under intensive study. Data from water in mines, tunnels, drill holes, hot springs, fluid inclusions, minerals and rocks suggested there are 5 sources of subsurface hydrothermal waters. Surface water including groundwater, commonly referred to by geologists as meteoric type of water. Oceanic water, formation water and deeply penetrating meteoric water, metamorphic water and magmatic water. Most formation of water, the water which is trapped in the sediments during the deposition may have been meteoric water originally, but their long burial in sediments and reaction with the rocks or minerals give it is a different character. Measurement of the relative abundance of the oxygen and hydrogen isotopes provides information on the sources of water as shown in the figure 3. But there are problems of interpretation of both the data obtained, both formation and metamorphic water produced by dehydration of minerals during a metamorphism may once have been meteoric water, but subsurface rock water reactions may change the isotopic composition, and if these reactions are incomplete, then a range of isotopic compositions will result. Another mechanism that may produce intermediate isotopic composition as the mixing of water, example magmatic and metamorphic. Example of some hydrogen oxygen isotopic studies are shown in the figure 4. Obtained values indicate that the main stage of mineralizing fluids at the Ag, Pb, Zn and Cu. Kaspalak mine Peru were magmatic origin, whereas for the post Bihon tungsten base metal deposit of northern Peru, the data suggested mixing of some meteoric or metamorphic or formation water with magmatic water during the mineralization, fluids for the formation of the cave in rock falcifer deposits. Illinois mines also produce zinc and lead minerals. According to isotope data are dominantly of the meteoric recharge formation water. Womonto 1986 described the main stage of sulfide mineralization in upper Mississippi Valley, USA to the oxen somewhat modified meteoric water. Present evidences thus appears to show that similar deposits can be formed from detectably different types of the water, and additionally that waters of at least 2 parentages have played an important role in the formation of some ore bodies. Information with regard to the source of dissolved components in hydrothermal solution can be obtained from isotopic data of helium and lead. For example, helium isotopic values of the ores from the Kaspalak and post Bihon silver base metal and tungsten base metal deposits of Peru indicate that ore bearing fluids are of mantle origin, thus suggesting the presence of magmatic fluids during mineralizations. Lead always contains a number of stable isotopes developed by the radioactive decay of thorium-232, urium-235 and uranium-238. Apart from non-radiogenetic lead, the lead isotopes have been used as tracer to seek the sources of the lead, and the studies have yielded some interesting results. For example, hydrothermal fluids responsible for depositing leading in the old lead belt of southeast Missouri in USA appear to have leached it from sandstone underlying the ore field, but a significant amount of the lead in the famous strata bound lead zinc deposits of the eastern and southern alphas, which are hosted by Triassic carbonates, appears to have been derived from feldspath in crystalline basement. Stacey et al. 1968 show that much of the lead in some lead fields of Utah was derived from associated igneous intrusions. The evidence from lead isotopic studies thus suggested that our fluids may collect their metals from magma if that was their sources. Alternatively, they may collect more metals from the rocks they pass through or obtain all the metallic content from the rocks they traverse, which can contain all the metals required to form an ore body. We must not, however, assuming that other metallic elements in a mineral deposit necessarily come from the same source as lead. Our present knowledge indicates that most of the rocks can act as a source of geochemically scarce elements which can be leached out under suitable condition by hydrothermal solutions because of the special relationship that exists between many hydrothermal deposits and igneous rocks. A strong school of thought holds that consolidating magmas are the source of many, if not all, hydrothermal solutions. The solutions are considered to be low temperature residual fluids left over after the pegmatite crystallization and contain the base metals and other incompatible elements that could not be accumulated the crystal lattices of silicate minerals preside by the freezing magma. Incompatible with the major silicate phases and are enriched in residual liquids, this module derives not only the water and the metals and the other elements from a hard body of igneous rock, but also it to derive the mineralizing system. The solution are assumed to move upwards along fractures and other channels way to cooler parts of the crust where deposition of minerals occur. How much water do magma contain? According to Burhana 1979, the water concentration is felsic magmas vary from 2.5 to 6.5 weight percentage with a medium close to 3 percentage. According to Whitney 1975, a rising monozogranitic magma which 3% of water will begin to exhale copious quantities at about 3.5 kilometer depth. Below these depths, water remains in the solution in melts because of the high containing pressure. As this magma crystallizes to produce a largely anhydrous mineral assemblage, an absolutely enormous volume of water can be given off by a cooling magma 1 kilometer by cube of felsic magma with 3% of water could exhale approximately 10 ml and Carrere 1987. Water is only one of the volatile components of late magmatic fluids. These are contains H2S, HCl, HF, CO2, SO2, H2. Of this H2S and HCl may be of particular importance. The solubility of H2O, H2S and HCl in granitic magmas are comparable and high H2S and HCl would be expected to fractionate strongly into exhaling aqueous phase. All base metals and many others can be extracted efficiently from a melt into exhaling aqueous phase provided that sufficient water is exhaled. Candela and Oline 1986 have shown that within a 3 weight percentage water content of the melt, about 95% of the copper in felsic magma would be extracted. Whether any granitic magma can produce economic mineral deposits under favorable condition or whether the ability developed to significantly rich mineralizing fluids is dependent on the sources region of magma evolution itself having a above normal concentration of the base and precious metals is at present under active debate. Hanana and Stein 1990 favor the first possibility and wrote as follows: the delicate relations between granite magma, its crystallizing phases, volatile content and species and oxygen fugacity plus The timing and mechanism of fluid release and the efficiency of the metal extraction ultimately control the formation of ore deposits. Several authors who investigated particularly deposits favor in magmatic origin for the hydrothermal solution that formed them, as recorded by in Henley 1991, as shown that December 1986, Mount Erebus, Antarctica discharged daily about 0.1 kilo Au and 0.2 kg copper, equivalent to 360 ton Au in 10,000 years. This and similar evidence from other volcanoes demonstrate the ability of the disgasing magmas to supply metals. In many ore fields such as the northern Penny ore fields and England, however, there are no acid or intermediate plutonic intrusions which might be source of the ores. Some of the workers have therefore postulated a more remote magmatic sources such as the lower crust or more frequently magmatic processes in the mantle, whereas another group of scientists favor deposition from formation of solution water which are trapped in the sediments during the deposition that has been derived up deep by the rise in the temperature and pressure caused by the deep burial. Such burial might occur in the sedimentary basins, and solution from the source are often called as baseline brine. With a geothermal gradient of 1 degree centigrade per 30 meter, temperatures around 300 degree centigrade would be reached at depth of 9 kilometer. Hot solution from the source are believed to reach metals but not necessarily sulfur from the rocks, though which they pass, ultimately precipitating them near the surface in self phases, carbonates on the fringe of the basin and far from any igneous intrusion. This too is a model favor at present by many workers, particularly as an explanation for the genesis of low temperature carbonate hosted lead, zinc, fluoride, barite deposits. It has been suggested that the available volumes of the formation of water are insufficient to carry the amount of metal that is present in such deposits. If the series objection to the model, then there is various hypotheses with which it may be refuted. Several workers favorable comparable flow of water under a hydrostatic head passing through sedimentary basin to produce the ore fluid, as shown in the figure 5. There is no problem of a lack of water for this model, and recent publication in support of it is to be found in Gravan 1985 and Betake 1986. Ancient geothermal systems as possible generation of the ore bodies are being actively considered. Geothermal systems form where a heat engine at depths about 3 km set deep groundwater in motion, as shown in the figure 6a. These waters are usually meteoric in origin, but some systems formation of other aligned waters may be present. System near the coast may be fed by sea water or both sea water and meteoric water. Magmatic waters may be added by the heat engine, and some ancient system appear to be dominated by magmatic water, at least in their early stages. Dissolved constituents may be derived by the circulating water from a magmatic body at the depth or from the country rocks which contain the system. This may altered by the solution to mineral assemblages identical with those found in some wall rock alteration zones associated with ore bodies. Common sulfides such as galena, sparolite, chalcoporite occur in a number of modern systems, example Salton Sea. The principal features of a geothermal system are shown in figure 6a. Meteoric water sinking to several kilometer depths, as shown in the figure 6a, enters in a zone high heat flow, absorb heat and rise into once or a succession of permeable zones. There may be outflow at an appreciated rate along a path such as one shown in the figure 6C are much slower outflow by penetration of the cap rock, example mudstone, tuff, etc. Outflow depends on the permeability of the rocks and the pressure at the top of the zone. If the outflow rate does not exceed that, all the inflow and all liquid system will prevail within a higher outflow rate. A stream pace will form and the stream pressure will decrease until the mass outflow is reduced to equal the mass inflow. A dynamic balance then obtains within the lower water level in the permeable horizon. Boiling water and the development of the convection currents in the water. Figure 6b illustrated that structure of a geothermal system in a volcanic terrain like that of a Tahoe volcanic zone, New Zealand. In this example, the hot waters are circulating through, reacting with probable obtaining dissolved constituents from both magmatic intrusion and the country rocks. In figure 6c and 6d, geothermal systems are postulated to explain vein tin and copper mineralization in and adjacent to the lands granite in southwest England. In figure 6e, geothermal systems are invoked to explain some of the differing types of the mineralization in southwest England and the zoning of the metals, that is one of the well known feature of this ore field. Recent geothermal work indicates that boron, lithium and tin in Cornish deposits, UK, was probably derived from the granites, whereas the copper and the sulfur were apparently leached from the country rocks, particularly shales. A similar model to explain epigenetic uranium mineralization of the Varkania mineralogical provinces of the Western Europe has been proposed by Catalonia 1982. Figure 7 shows schematic for the formation of two types of epithermal precious metal deposits in volcanic terrains based on Held et al. 1987 and Henley 1991. A detailed application of this model to epithermal precious metal deposits, it is found to Abaya et al. 1986. It is to be noted that although hydrothermal deposits are only small geological features, fossil geothermal system can be very large. Means of transport. Sulfides and other minerals have such low solubilities in pure water that is now generally believed that metals were transported as complex ions. A few simple figures will illustrate this. The amount of zinc in a saturated zinc sulfide solution at pH of 5 and temperature of 100 degree centigrade is about 1 into 10 to the power of minus 5 grams per liter. A small ore body contain 1 meter of zinc could be formed from a solution of this strength, assuming all the zincs was precipitated. Provided that 10 to the power of 17 liters of solution passed through this body, this is equal to the volume of a tank having an area of 10,000 kilometer square and size of 10 kilometer, high an impossible quantity of solution. Laboratory thermodynamic studies and examination of the modern geothermal solutions have led geochemists to conclude that metals are transported by hydrothermal solution as complex ions. That is, the metals are joined to complexing groups. The most important ligands are hydrogen sulfide, chloride, OH. Other ligands including organic ligands may also contribute to complexing in ore fluids. Bisulfide complex can exist stable near neutral solution containing abundant H2S. Ions such as PBS are formed and these have much higher solubilities than pure ionic solution. The main objection to what is very useful and promising hypothesis is the high concentration of H2S and HS required to keep the complexes stable, a concentration much higher than that usually found in hot springs. Fluid inclusions and geothermal systems. For this and other reasons, many workers favor the idea of the metal transport in chloride complex such as AgCl2 and PbCl3. It is likely, however, the both and other complexes play a part. Metal transportation. Bisulfide complexes may be important for ore transportation at temperature below about 350 degree centigrade. Henley et al. 1984 suggested that cold probably travel as bisulfide complex up to about 300 degree centigrade, but the chloride complexing may be important at higher temperature. Seward 1991 has pointed out the although AuHS4 will play an increasing disseminated role in gold transport at temperature above 300 degree centigrade. Sulfide complexes as a whole may still be important carriers of gold. For example, the very stable AuH complex may be important at temperature about 300 degree centigrade. The origin of sulfur and the site of deposition is also a problem. Did it originate at the site or was it carried there with the metal in solution? Some mineralization situation seem to be determined that sulfur and the metal travel together. Isotopic evidences from the modern geothermal systems, ocean floor fissures, venting hydrothermal solution and evidence from some fluids inclusion also favor this interpretation for many deposits. If ore metals are transported as bisulfide complex, then abundant sulfur will be available for the precipitation of sulfide at the site of depositions. Lateral segregations. It has been accepted for the many years that the quartz lenses and veins in metamorphic rocks commonly result from the infilling of dilatational zones and open fracture by silica which has migrated out of the enclosing rocks, and that the silica may be accompanied by other constituents of the wall rocks including metallic compounds and sulfur. This derivation of the materials from the immediate neighborhood of the vein is called as lateral segregation. In figure 8.a is a vein forming from the hydrothermal solution supersaturated in silica. Some of this diffuses into the wall rocks and causes some silicification. The curve showing the level of the silica decreases away from the sources. In figure 8.b, the opposite situations exists where silica is being supplied to the vein from the wall rocks. The curve now climbs as it is less than the vein, indicating a zone of the silica depletion in the rock next to the vein. Clearly, silica has been abstracted from the wall rocks and presumably as accumulated as vein. A very interesting example of deposits formed in this way has been described by Boyle 1959 from the yellow knife gold field of the Northwest Territory of the Canada. The principal economic deposits of the yellow knife field occur in the quartz carbonate lenses in extensive chloranitic shear zones cutting amphibolites. The deposit representations concentration of the silica, carbon dioxide, sulfur, water, gold, silver and other metallic elements. The principal minerals are quartz, carbonates, cercites, pyrite, arsenopyrites, stibnite, chalcopyrite, sparolite, porotite, various sulfur salts, galena, skillite, gold and aurostibnite. The regional metamorphism of the host rocks varies from amphibolite to green schist facies. Alteration alloys or carbonate silicate, schist and chloride carbonate schist occur in the host adjoining deposits. It is very instructive to remember that the dominant minerals of the veins is quartz. The profile of the silica alongside the lens is shown in the figure 9. This demonstrated that a very substantial amount of silica has been subtracted from both the alteration zones, and this has occurred on both sides of the vein. Clearly, more silica has been subtracted from the wall rocks than is present in the lenses, and the problem is not whereas the silica in the lenses came from, but whereas the surplus silica gone to. Some subtraction of the magnesia, iron oxides, lime, titanium and manganese oxide has also been occurred, and doubtless these sources of iron in such minerals as pyrite, porotite and chalcopyrite in the lenses. Alumina shows a depletion in the outer zone of alteration and concentration in the inner zone where it is collected for the formation of sarcosite. A similar depletion in these elements has been reported from wall rock alteration beside the gold veins of the Saima mine, Cuba, Canada in 1986. As a result of the extensive development of a carbonates in the alteration zones, carbon dioxide develops to a much higher level than in the unaltered country rocks. Water show a similar but not identical behavior. Bailey produced good evidence that CO2 and H2O2 were passing through rocks in the considerable quantity, being mobilized by the regional metamorphism and migrating down the metamorphic phases. They passed into the shear zone to form the chloride, carbonate and sarcosite. It appears highly probable that the major constituent of the shear zones resulted from the rearrangement and introduction of the material from the country rocks. The remaining question is whether the metabasalts could have been the source of the sulfur and metallic elements in the deposits. The metabasalts consist of metamorphosed basic volcanic lavas and tuffs. The rocks are richer in elements such as gold, silver, arsenic, copper, etc. than other igneous rocks, and for the unsheared metabasites of the yellow knife area, Bailey obtained the following values all in ppm: sulfur 1500, As 12, stibnite 1, copper 50, Au 0.01, Az 1. For the purpose of calculation of the rock system was taken to be length is 16 kilometer, width is 152 meter, depth is 4.8 kilometer. The amount of ore in the systems was assumed to be 6 into 10 to the power of 6 tons with average grade of S is equal to 2.34 percentage, As is equal to 1.35 percentage, Sb is equal to 0.15 percentage, Cu is equal to 0.07 percentage, Zn is equal to 0.28 percentage, Au is equal to 0.654 per ton and Ag is equal to 0.139 per ton. The total contents of these elements in the system prior to shearing and alteration in the deposits are shown in the table 1. It is apparent from these figures that all the elements considered to be derived slowly from the shear rock of the shear zone, and there is no need to postulate another sources. Indeed, there is such a difference between the values is almost 2 or 3 in table that may be well be that significant quantity of the chalcolite elements accompanied by surface silicon to higher zones in the crust to form deposits which have now been eroded away. Other application of the lateral segregation theory in very different geological setting include Brimala 1979 and Dijongala at D. Olge 1981, Brimala 1971 as proposed that main veins in Butte, Montana, USA were formed by the concentration of ore forming materials already present in the host grano direct intrusion in the form of protara. So, Dijongala and D. Olge 1981 have discussed the formation of a Pb, Zn, Cu bearing veins in the carboniferous sediments in Belgium in terrains of this theory. Finally, it can be noted that even low grade metamorphism, lower green schist phases permits the subtraction of a 50% of the gold content of the andesites. Dosala and Dupuy 1987. Other references and review of segregation theory can be found by Bailey 1991. Metamorphic processes, contact and regional metamorphism. Isochemical metamorphism of many rocks can produce materials having an industrial use. An obvious example is marble, which may be produced by either contact or regional metamorphism, or pure and impure limestones and dolomites. Other important industrial materials of metamorphic origin are slate, asbestos, corundum, emerald, garnet, some gemstones, graphite, magnesite, pyrophyllite, sillimanite, talc and wollastonite. Alkochemical metamorphisms may accompany contact or regional metamorphism. In the former case, in particular, it may lead to the formation of skarn deposits carrying economic amounts of metals and industrial minerals. The role of other metamorphic process in ore formation. In this section, we are concerned with those metamorphic changes that involve recrystallization and redistribution of materials by anionic diffusion in the solid state through the medium of volatiles, especially water. Under such conditions, relatively mobile ore constituents may be transported to sites or lower pressure such as shear zones, fractures or the crust of the folds. In this way, the quartz chalcopyrite pyrite veins in amphibolites and schist and may gold veins in greenstone Archean belts were possibly generated. The behavior of trace amounts of ore minerals in large volume of rock undergoing regional metamorphism is uncertain and is a field for more extensive research. It may be thought that with the progressive empelagments of large volume of water and other volatiles during the prograde metamorphism, natural hydrothermal systems might evolve that would carry away elements such as copper, zinc or uranium, which are enriched in trace amounts in pellites. D. Vorra 1955 calculated that during the transformation of 1 cubic mile of epidote amphibolite phases or the blendite into granulate phases, there may be a release of 9 million tons of Cr2O3, 4.5 million tons of NiO and 900,000 tons of CuO. Similarly, retrograded metamorphism can release large quantity of zinc, lead and manganese. Recent studies of mass balance changes accompanying the development of foliation in metamorphic rocks have shown that regional metamorphic terrains are large hydrothermal system analogs to the smaller scale system in young oceanic crusts. These systems have the capacity to leach a wide range of components including ore forming materials from a very large volume of crust. For flow to take place in such systems, regional permeability must be developed. It is known that major roles in enhancing a rock permeability are played by the development of grain scale, dilatancy and mineral filled fractures. Both the features result from rock fracture, but on very different scales. In this fluid flow is channeled through a small volume of rock in which dilatant zones develop, then mineral deposits may be formed. 5 of Henley 1973 considered just such a mechanism. They envisaged a situation where volcanic sedimentary pile is being metamorphosed under amphibolite phases conditions. It would be losing about 2% water, and if salt is present and oxygen is buffered by the magnetite ferrite silicate assemblages, then gold solubilities of order of 0.1 ppm at 500 degrees centigrade would be achieved. This gold would either be dispersed through greenschist phases rocks or concentrated into favorable structure. This could happen if the solution flow was focused in a large vein or fault system where seismic pumping could have forced the ore fluid upward. Fife and Henley 1973 showed that a source region of 300 km³ could have provided all the gold, silica and water required to form a deposit as large as Morro Velho, Brazil. This model of the gold mineralization is similar to that proposed by Boileau, data provided earlier, but now the major constituents are derived from a deep source region and not by the lateral segregations. This model and variation of it have been used to explain the formation of a number of gold deposits by various workers including Geology and Freire 1979, Mine, Abidite Greenstone Bill, Philippines et al. 1994, Archean banded iron formation hosted gold deposits. Sifford and Allen 1985, Metallurgeonis in the Herches Doma, North Wales, UK, Annals and Roberts 1989, Turbotite hosted gold mineralization at the Dolochi Mines Defido, Wales in UK, and Williams 1990, gold mineralization Cumulates and Cumulata, Cuba, Canada. A recent counter blast to this metamorphic model for the genesis of hydrothermal gold deposition solution has come from Burroughs et al. 1986. We have used a great deal of carbon isotope data from the world's two largest Archean gold, vein and shear zone systems, Olainara Mecanita in Canada and the gold mile in the Western Australia, to support a return to the once orthodox hypothesis of a magmatic hydrothermal origin of the mineralizing solutions. They have a support from a number of workers including Siddhaya, Rajamani 1981, Kolar Deposit of India, Cameron and Attari 1987 produce evidence for the presence of oxidized fluids during the formation of a number of Canadian and Australian Archean gold deposits, such as fluids they concentrated can only be magmatic origin. Example of other deposits considered to have formed from metamorphic fluids include uranium deposits in Sweden, cobalt tungsten mineralization in Queensland, Illawarra zinc, lead, silver, massive sulfide ore body, New South Wales, the copper ore bodies in Mount Isa mine, Queensland, Australia, SBAU ore bodies along the antimony line shear zone, Murgenia schist belt, South Africa. Summary of the topic: minerals deposits owe their origin to internal and surface processes. Internal processes include magmatic crystallization, example diamonds disseminated in kimberlites, REE minerals in carbonites, magmatic segregation and liquations, example stratiform chromite in ultramafic rocks, nickel sulfide ores associated with comatites, precipitation from hydrothermal fluids, lateral segregation, metamorphic process, orthomagmatic deposits formed by fractional crystallization are usually found in plutonic igneous rocks, and those produced by liquations may be found associated with both plutonic and volcanic rocks. Hydrothermal deposits were formed at temperatures ranging approximately from 650 degree to 50 degree centigrade. Hydrothermal solutions are derived from 5 sources. Number 1, surface water including groundwater, commonly referred to as meteoric water. Number 2, ocean or sea water. 3, formation water, the water trapped in sediments during the deposition and deeply penetrating meteoric water. And 4, metamorphic water, water released during the dehydration of minerals. And finally, 4, magmatic water. Hydrothermal fluids collect their metals from magma and are the rocks they pass through. Concentration of water in felsic magmas vary from 2.5 to 6.5 weight percentage with a medium close to 3%. Water is only one of the volatile components of late magmatic fluids, which also contain H2S, HCl, HF, CO2, SO2 and H2. Geothermal systems form where a heat engine, usually magmatic, at depths of a few kilometers set deep groundwater in motion. The water can be any source: meteoric water formation, water, sea water. Hydrothermal solution of geothermal system may contain magmatic water admixed with waters of other sources. In hydrothermal solutions, Metals are transported as complex ions, that is, the metals are joined to complexing groups. The most important ligands are HS or H2S, Cl and OH2. Other ligands including organic ligands may also contribute the complexing in ore fluids. Bisulfide complex may only important for the transportation at temperature below 350 degree centigrade. At higher temperatures, metal transport may take place as chloride complexes. According to Boyle 1959, gold mineralization in yellow knife gold field of northern territory of Canada was developed as a consequence of lateral segregation. SiO2, S, H2O, L2O3 oxides of magnesium, iron, calcium, titanium, manganese, As, Au. Au was subtracted from shear zones adjoining both the sides of auriferous veins. Isochemical metamorphism of many rocks can produce materials having an industrial use. Important industrial materials of metamorphic origin are asbestos, corundum, emery, garnet, graphite, magnesite, ferrofluoride, sillimanite, talc and others. Metamorphic process during ore formation include recrystallization and redistribution of materials by ionic diffusion in the solid state or through the medium of volatiles, especially water. Under such conditions, relatively mobile ore constituents may be transported to sites of lower pressure such as shear zones, fractures or the crest of folds. Regional metamorphic terrains are large hydrothermal systems, and these systems have the capacity of leach a wide range of components including ore forming materials from a very large volume of crush. If the leached components as channeled through a small volume of rock in which dilatant zones develop, then the mineral deposits may be formed.